Okay, it's a great pleasure for me to introduce today's speaker, Professor Dave DeMille from Yale University. He's been a professor of physics there since 2004, but he wasn't always at Yale. He started his work, well, I guess he was an undergraduate at the University of Chicago, but he started his PhD work at Berkeley in the group of Gene Cummins, where he did a pioneering experiment on the search for the electron EDM, which what we call in the EDM is the thallium experiment. So Dave was a PhD student on the thallium experiment and built a large portion of that apparatus. That thallium experiment gave a result which stood for approximately 10 years, 12 years, as the best EDM limit. There still is no evidence for a non-zero electric dipole moment of the electron. If you're not familiar with this, that means that the chances of LHC finding anything are almost zero. Just kidding. But it could be true. Anyway, so it's a very important result, and it was, but Dave continues to hold, along with his collaborators, the record for this. He's part of the ACME collaboration, and that's one reason why he's no stranger, because he comes up here to work on the ACME experiment every couple of weeks, physically and electronically every week. Come and see him. Dave has been a pioneer in using atomic tools, what we call atomic tools. I don't know why we call that anymore. All these are is lasers doing some kind of coherent transition, or maybe microwaves doing a coherent transition. But using these kind of coherence tools to study particle physics. This includes parity violation and many other things. But not only that, he also has been a pioneer in two areas of making ultra-cold molecules. One, the joining of atoms, ultra-cold atoms into polar molecules, and the other, which you'll hear about today, is laser cooling of molecules. And I think you and Junyi are the only two that have done both techniques in their labs. And that's pretty good company to be in. So Dave is an amazing guy, and I'm just repeating what other people tell me. I know he's amazing, but everybody who comes, eventually, they always kind of come up to me eventually after, oh, Dave's really an amazing guy. I go, yeah, I know, he's amazing. He is. And we're very, very happy to have him here at Harvard, collaborating with us, and very happy to have him here today.
Well, thanks for the amazingly flattering introduction, John. Well, yeah, thanks to all of you for coming. So as John said, I'll be telling you today about some work that we've been doing in my group over the last few years, where we've been learning how to directly cool and trap diatomic molecules in a way that's really directly analogous to the ways that we know and love for laser cooling and trapping of atoms. So brief outline of the talk, I'll give a little bit of overview of motivation, talk a little about early results where we were able to start laser cooling and using radiation pressure slowing of a beam of strontium fluoride molecules. Then more recent work where we've now been able to make MOTS of strontium fluoride molecules. Then I'll actually spend quite a bit of time on outlook, because we're now, as these techniques are starting to work in a way that's closely analogous to what we're used to for atoms, the possibilities of what to do are looking more and more interesting. I'll also say as preface, this is a difficult audience to prepare a talk for, because I know a fraction of the audience are the world's super experts on cooling molecules from John's group, and then probably lots of people who've never thought about a diatomic molecule in their life. So I split the middle, and hopefully everybody will be disappointed by the end. Right. So just as a broad overview, of course, methods for cooling and trapping atoms have really been a scientific revolution. But if you start to think about molecules, what you realize is for molecules even more than for atoms, getting colder is better. Unlike atoms, molecules have lots of internal states which are typically populated thermally at any non-cryogenic temperature, even at cryogenic temperatures. So if you can cool down the internal degrees of freedom, the rotational and vibrational and hyperfine degrees of freedom in a molecule, then you can collapse the population in a Boltzmann distribution, in principle all the way down to the lowest state, and just get bigger signals for any sort of experiment where you're doing quantum mechanics and starting from one particular quantum state. As John said, I've spent a lot of my life doing precision measurements, which are ultimately spectroscopic measurements. And of course, just if you can cool the motional degree of freedom, then you eliminate Doppler broadening, get higher resolution, and can measure energy levels more precisely. And then sort of in many ways, the ultimate goal for cooling and trapping for molecules, much as for atoms, is to get them cold enough so that you can hold them in some weakly perturbing trap. Then you can, in principle, if you get them cold enough, fully control their quantized motion, and also be more and more sensitive to weak effects such as energy shifts that are of interest in particle physics. But also in a very general way, we've learned from condensed matter physics and atomic physics that every time you get into a new regime of temperature, new phenomena appear and more control is available. So this is a worthy and ongoing goal for the field is to make molecules ever colder. So that said, there are lots of specific applications that have been envisioned that are specific to molecules or where molecules have some interesting new features as compared to atoms. And this plot is from a reviewer article that wrote with a few other people several years back. That's a phase space density plot, so decreasing temperature to the left and increasing density going up. And this shows some of the many ideas that people have talked about where molecules provide some new and interesting feature compared to atoms. So, for example, at the very highest phase space densities in the regime of quantum degeneracy, there's lots of interesting physics, much of which is driven by the fact that if you have polar molecules, you can apply an electric field, polarize them, and then their electric dipole-dipole interactions are orders of magnitude stronger than typical interactions between atoms. They also operate at much longer range. So this means that you can get very interesting, strongly correlated many-body states, such as dipolar crystals, and in general, dipolar quantum gases. There are also applications to quantum information, and lots of interesting new possibilities at looking at chemical reactions at these extremely low temperatures. But even at more modest phase space densities, down here in this blue bubble, there's interesting physics that I have a special interest in, where molecules have been shown to amplify effects of fundamental symmetries such as parity violation or CT violation. And there, being colder is better, but also what matters is being able to get lots of molecules. So that'll be a theme throughout my talk, is both to get high phase space density, but also to get as many molecules as possible in your experiment. I'll also point out that for many of these applications, what you really care about or for many of the applications, what you want is a simple molecule. So something that's sort of the high school chemistry version of a polar molecule with charged balls on a stick, a structureless electric dipole. That's perfectly sufficient for many of these applications. However, for some of the applications, particularly ones that are aimed towards physical chemistry at low temperatures, you really like to be able to access many different kinds of molecules, many different species. And for many of these applications, there's a specific need for molecules that have unpaired spins. So for example, John mentioned our ACME experiment where we looked for the electron's electric dipole moment, because the electron, if it has an electric dipole moment, it has to be along the spin axis. You need to work with a molecule where the spins are not paired off into closed shells. And again, for many of these applications, these unpaired spins are crucial. And so far, the techniques for producing ultra-cold molecules with unpaired spins are rather less well developed than they are for the more structureless dipoles. So as you'll see, our experiments use species like this. And just to hammer that home, again, applications of molecules with unpaired spins include electron-electric dipole moment searches. John mentioned this briefly. We have an experiment where we're using molecules with unpaired spins to study electroweak physics, essentially to see how the strong interaction modifies a particular coupling of Z bosons to protons and neutrons. And this takes advantage of the fact that we can have opposite parity states that are mixed by the weak interaction and tune them to near degeneracy using a magnetic field coupled to the electron spins in the molecules. And that near degeneracy means that a tiny perturbation is enhanced because perturbations depend on a mixing divided by an energy difference. So we can use the molecules to get a tiny energy difference and really a macroscopic effect of electroweak induced parity violation in a molecule. There are also interesting many-body physics such as simulation of lattice spin models that where the ideas rely on having unpaired spins connected to electric dipole moments of molecules. So this has been some of our motivation for being particularly interested in these species with unpaired spins. Okay, so that gives you some sense of motivations for these experiments. How do you do it? And I borrowed this slide from Junyi. He points out that there are two ways to make molecules. You can either cool your atoms and then stitch them together to make molecules using some reaction, or you can make your molecules and then cool them down. And of course, many of you are probably aware of the beautiful experiments from Junyi and Debbie Jin's group, and now follow-on experiments from Innsbruck and Durham, and now Martin Spierlein's group at MIT, with really tremendous success in stitching atoms together to form molecules. But what I'll be telling you about today is trying this separate route of starting with the molecules and cooling them down. So here's the space-based density plot again. And as I mentioned, it's now possible, several groups have demonstrated that it's possible to make more or less structureless dipoles in the regime of quantum degeneracy using Feshbach resonance techniques. But then in the meantime, many groups, including John Doyle's as one of the leaders in this field, have been starting with molecules and trying to cool them down. And there are a variety of different techniques that in their initial phases were giving rather modest space-based densities, but were much more general, could really address lots of different types of molecules. And now many of us are focused on trying to start with these techniques and push to the regime of higher phase-based density and also more molecules. So techniques such as laser cooling that I'll tell you about, but also techniques I won't tell you about, like evaporative cooling that's now been demonstrated by Junyi's group. Sympathetic cooling is something that many of us are interested in trying, but still hasn't been demonstrated for molecules. And really, this is the heart of the talk, is how do you start with essentially cryogenic type temperatures and move to the lower temperatures that we're used to for atomic systems. So it seemed natural to think about laser cooling molecules, and if you've never thought about this and then you take a quick look at it, you'll quickly understand that laser cooling molecules looks pretty hard. So why is that? Well, the reason is that for laser cooling to work, you need a cycling transition. You need to scatter typically of order 1 million photons from your system in order to transfer enough momentum to slow down and cool, starting from room temperature, for example. So with atoms, we know and love cycling transitions in alkali or alkaline earth atoms, where you excite the atom and then it comes back to the same state and you do it again and again and again. So if you try to do this with molecules, where these are indicating rotational states, you immediately realize there's going to be a problem, which is because there are additional rotational states in the ground state, selection rules ensure that this j equals 1 rotational state can decay back to where it started, but also to other states, such as this j equals 2 rotational state. Well, that doesn't look so bad. We know how to deal with that with atomic systems. We had a repump laser, so okay, we need 2 lasers so far. But in addition, molecules have vibrational structure, and unlike the rotational transitions where quantization of angular momentum gives you well-defined selection rules, the vibrational states in molecules have no well-defined selection rules. The probability to branch into excited vibrational states is determined by Frank-Condon factors, the overlap of the excited and ground state vibrational wave functions. And if you pick 2 random atoms out of the periodic table and look at the diatomic molecule that's made of them, if you excite an electronic orbital in the molecule, typically it will decay to a dozen or more different vibrational states. So the common wisdom up until, well, not so many years ago, 7 or 8 years ago, was that there was really no way around this short of having dozens of lasers. But it turns out that for a surprisingly large class of molecules, including one that we just heard about from Ivan Kaziria from John Doyle's group, that this branching into vibrational states is actually not so bad. It can be held under control. So we've started using strontium fluoride, which is one of this class of molecules where the vibrational branching is not so bad. In our case, we start with our molecule in its ground state, which is a state which is somewhat analogous to the ground state of an alkali atom, like an S1/2 state. We excite it to the lowest excited state, which is somewhat analogous to the P state of an alkali atom. It's at a nice convenient wavelength accessible with diode lasers. And then this state can decay down to different vibrational levels. But the probability to decay to different levels falls off very rapidly. So, for example, 98% of the time this state will decay back to where it started, and then we can hit it with another photon. After about 50 photons, it will decay into this first vibrational state, so we'll have to repump that. But if we repump that, then we can scatter about 2,500 photons before it lands here, and you can see the decay into different vibrational levels is increasingly suppressed. So this is an example of this class of molecules where only a few lasers are needed to repump out of vibrational levels. And really this was a seminal paper by Mike DeRosa from Los Alamos who pointed out that there is this class of molecules for which this is possible. In our case, we add one repumping laser to get out of the first vibrational level. Crucially, and I'll discuss this later, crucially, this state connects to the same state that we use for the optical cycle, and that turns out to cause some trouble. This second vibrational level, which we decay to only after scattering 2,500 photons, we repump through a different vibrational level, and likewise for the third vibrational level, we repump through the second vibrational level in the excited state. But the bottom line here is that it only takes 4 lasers in this system to scatter 1 million photons, which is enough to do basically everything that we're used to for cooling and trapping of atoms. And of course, for alkali atoms, we're used to using 2 lasers, one main laser and one repumper, so 4 diode lasers doesn't sound so daunting. Nevertheless, if you use the scheme for rotational excitation that I mentioned before, you'd have to multiply this by 2 and need 8 lasers to get started, and that sounds pretty daunting. But back when what initiated our work on this was a nice paper from Junyi's group, which pointed out that if you're clever, you only need 1 laser to deal with the rotational states. And here's the idea: if instead of exciting from the rotational ground state up to a state with angular momentum 1 that can decay down to 2 and back to 0, if instead you start from a state with angular momentum 1 and excite to a state with 0, selection rules ensure that you can only go back to the state with angular momentum 1. So this means you don't have this doubling in the number of lasers, you only need 1 laser per vibrational level. And that really was enough to make us think that this is feasible to try. This sounds great. Sorry, let me go back here. This sounds great, and it is great. It's what we do, but it comes with a hidden problem, which is, in fact, has turned out to be a much more central issue in laser cooling of molecules than the vibrational branching, which everyone thought was always going to be the hard part. So let me explain that a little bit. If you drive this sort of 1 to 0 transition, no matter what polarization you use, here I've used the example of a pi polarization, but it's true in any polarization. One of the sublevels in the ground state will be bright to the excitation, but 2 of them will be dark. And so after you scatter 1 photon, 2/3 of the time you land in one of these dark Zeeman sublevels. If you want to have a cycling transition, which you need for laser cooling and trapping, you need to somehow get the population out of these dark states that you optically pump into back into the state which is bright and can be excited by the laser. So we've done this in a number of ways. In our case, our molecule has an unpaired spin, so we can use a magnetic field to hook to it and Larmor process from bright states to dark states with a magnetic field. You can also rapidly switch the laser polarization back and forth. We've done that, that works. Or you can take advantage of the fact that the molecule has extra states, like this other rotational state. If it's a polar molecule, you can drive transitions between these levels with resonant microwaves, and we've done that, and that works as well. So this is something you have to deal with, but there are a number of ways to take care of it. But there's a subtle problem with this, which is that these additional levels that you're constantly having to push population out of to get back into the optical cycle ends up reducing the optical forces that you can apply. And it's pretty simple to understand that. If you have a beautiful, simple two-level system like in an alkali atom, if this state has lifetime tau, or if this state has lifetime tau, then the maximum rate at which you can scatter photons is if you're rapidly Rabi cycling, half the population is in the excited state, and then the maximum scattering rate is one half the decay rate of this level. In the case that I just told you about, if you have these dark Zeeman sublevels, it's not too hard to convince yourself that the best you can do in terms of scattering photons and therefore applying optical forces is to mix these levels back into the cycle as fast as you can. And if you do that, then the populations equalize among all these levels, and now you only have a quarter of your population in the excited state, and the rate at which you scatter photons is only a quarter the decay rate of this state. So the forces are half as big as you can get in a two-level system. It's even worse when we have to do what we have to do, which is when we populate this first vibrational level, the only route we have to repump this into the optical cycle is through the same excited state. That means that when population decays here, it gets stuck unless we push it around as fast as we can. And again, it's not hard to convince yourself. The fastest you can scatter photons is obtained when you equalize the population in all these levels, and then the maximum scattering rate, and therefore the maximum optical force, is down by a factor of 3.5 or so compared to the case of atoms. So what this means is we're always fighting against having much smaller forces than we're used to in atomic systems. And that adds up in experimental complexity pretty quickly. So in part to combat that, we found that it's really key to start with molecules that are not too hot to begin with. So we've used this technology that's been developed over the years in John Doyle's group, especially by Dave Patterson, for making cryogenic molecular beams. So the idea is that we inject hot molecules by laser ablation of a solid target into a cell that's held at cryogenic temperatures. It thermalizes with a buffer gas, and then it's swept up in a wind and forms a beam that comes out at a relatively low velocity. In our case, we use helium at 4 Kelvin, and the velocity is below 150 meters per second typically. So having that initial low velocity is crucial because our forces are so weak, otherwise it would take us an enormously long path to slow molecules down. And this has proved to be a really key technology for many experiments in the field, including our ACME experiment and a new one that I'll tell you about at the end of the talk. So this not only gives us beams that are moving slowly, they're also internally cold because of the cryogenic temperature and some expansion cooling. And also this wind that picks up the molecules and pulls them out the cell gives you unusually high fluxes for the type of molecules we're interested in. So that's our starting point. Let me tell you some of the ugly details about strontium fluoride. So I've been giving you a simplified picture, which is complicated enough because it's a molecule, but the reality is even more complicated. Here's a simple picture that I've been giving you, a rotational state with angular momentum 1 being excited to a state with rotational angular momentum 0. But in fact, these states have unpaired electron spins. So there's a spin-rotation coupling, analogous to spin-orbit coupling, but much, much smaller. And then the fluorine has a nuclear spin of 1/2, so there's hyperfine structure associated with that. In the end, this n=1 rotational state has 4 resolved hyperfine sublevels, split by a total of about 170 megahertz. So it turns out this is not so hard to deal with. We take our laser and send it through electro-optic modulators that give sidebands that hit all of these transitions simultaneously. So that allows us to address all of this substructure with one laser beam. However, it's extremely power hungry. We have to have lots of power on each of these sidebands. So it's necessary to have higher laser power than we typically need for atomic cooling experiments. So back in ancient history, back in 2010, we were able to get our first demonstration that this basic idea works for strontium fluoride. So here we started with one of these cryogenic buffer gas beam sources, shot a beam of strontium fluoride from left to right in the picture, and our first goal was just to demonstrate that laser cooling could work. So we were interested in cooling the transverse motion of the molecular beam. It's initially collimated, so it has a relatively small transverse velocity width in this direction. Then we hit it with cooling lasers, which bounce back and forth in a multi-pass mirror system. This is meant to extend the interaction time, given that the forces are quite weak. It takes a long time to exert enough force to cool the molecules. But then we probe what's happening by having a probe laser beam and imaging the fluorescence. So the idea is that we see a fluorescence image that tells us the transverse spatial distribution, but of course that's linked to the transverse velocity distribution as the molecules fly through the apparatus. And here's what typical data looks like. So the black trace is a transverse spatial image, or transverse spatial distribution of the unperturbed molecular beam. The red image is what happens if we tune the laser to the red of the transition and do standard Doppler cooling. And here it's very evident that we've reduced the velocity spread. You can see the area of these curves is the same, so we haven't lost any molecules despite having scattered many hundreds of photons. And this gave us a final temperature of about 5 millikelvin. We also rediscovered an old effect of subdoppler cooling, a particular Sisyphus cooling mechanism that happens with blue detuning. And in that case, we were able to get down to temperatures as low as about 300 microkelvin. So this was the very first demonstration that laser cooling could be applied to a molecule. It's in a very modest way because we've only cooled the transverse motion, which was already fairly cold because we limited the spatial extent. But it was encouraging because the temperature here was limited by the finite interaction time of the laser. We hadn't hit any, as far as we could tell, we hadn't hit any ultimate cooling limits. And just for reference, the Doppler temperature for strontium fluoride is about 200 microkelvin. So yeah, Doppler cooling, we just didn't have enough time to get down to the Doppler limit. Right, so because we're interested in not just cooling the transverse motion, but actually also trapping the molecules, we need to slow them down enough to be able to trap them. To do that, we use again, a sort of ancient technique from atomic cooling and trapping that had been abandoned because it wasn't useful, which is called white light slowing. So the idea is we try to have a very broad spectral profile of the lasers that are hitting the molecules, counterpropagating to them, to account for the shift of the Doppler shift of the molecular transition as the molecules are slowed down by being hit with the laser. So this is what we wanted our laser frequency to look like, with a sharp intensity cutoff so that any molecules with a low enough velocity would be Doppler shifted out of resonance and wouldn't be hit by the lasers anymore. Here's what we actually get by sending the laser through a 5-degree EOM and driving it very hard. So it's not quite this top hat profile, but it's a pretty flat spectrum and pretty dense over a range of about 400 megahertz. So here's the experimental setup. Molecular beam, again traveling from left to right, slowing laser with all the associated vibrational repumping lasers counterpropagating to push against the molecules and slow them down. And this works quite well. So here's the longitudinal velocity profile of the unperturbed beam. As promised, you can see the peak is at 120, 130 meters per second. Then when we turn on the slowing lasers with things optimized at this stage of the experiment, we saw a velocity distribution that looked like this. And this was quite encouraging to us because we had a clear non-zero number of molecules down at velocities below about 10 meters per second, which is comparable to typical capture velocities for a magneto-optic trap. It made us think that this was going to be good enough to load molecules into a trap. Nevertheless, you can see here, unlike for the transverse cooling, the integral of this velocity profile is definitely reduced from the laser slowing, and there's really not so many in this low velocity tail. So the key point here is this white light slowing technique is really very low efficiency. Unlike what we're used to for atomic methods such as Zeeman slowers, with a white light slowing, there's no reason why the final velocity is correlated with the position where that final velocity is obtained. So typically molecules will either be slowed before they get to the trapping region or after, and only a tiny fraction of them get slowed where we want them in the trapping region. In addition, as the molecules are slowed down, the beam diverges more and more. So really the fraction of the molecules that came out of the source that ends up having a low velocity at the right position is tiny, and you'll see that reflected in our later results. Right. Nevertheless, we had enough that we believed that we should be able to make a magneto-optical trap, much as we know and love for atoms. But it was immediately clear conceptually that things were going to be different for molecules. Let me try to explain why. So the typical canonical picture for how to make a MOT with an atom is to make a transition from a state with angular momentum J to an excited state with a higher angular momentum, J plus 1, such as an S to P transition. And of course you have counter-propagating opposite circular polarizations. You have a magnetic field gradient with a 0 in the center. And the idea is that if your atom is over here on the right with a magnetic field in the positive Z direction here, then the Zeeman shifts are such that you will preferentially scatter a sigma minus photon and get pushed back towards the center. When you do that, you land back in the ground state and you get to do it again. Of course, if you're on the left of the picture, the magnetic field is negative. The Zeeman shifts are such that you are shifted closer to resonance with the sigma plus light, and you again get pushed towards the center, and you land in the same state that you started in. So everybody in this audience surely knows this MOT picture very well, and it works beautifully. By contrast, if you have the kind of structure that we have, where the ground state has an angular momentum that's bigger than the excited state, like a 1 to 0 transition, then you can imagine setting up the same thing, where you have counter-propagating circular polarizations, a magnetic field gradient, and if you're over here on the right, if you start at this level, you'll Zeeman shift closer to resonance, you'll absorb a sigma minus photon, get kicked towards the center. The problem is that you'll then decay to these other Zeeman sublevels. At least a third of the time you'll decay into this m equals -1 level. The only way to get out of this level is to absorb a sigma plus photon, which kicks you in the wrong direction, away from the trap center. And not only does that do the wrong thing, but it takes a long time to do the wrong thing because you're shifted very far away from resonance. So it's not at all clear from looking at this picture that you should expect there to be a restoring force for a MOT like this. In fact, there was a nice paper by Mara Prentice and Nick Bigelow when he was her student here that showed for this kind of system, the force identically vanishes. Pretty simple theoretical paper. Nevertheless, people who seemed unaware of this theoretical result did the experiments in atomic MOTs on D1 lines, J to J-1 transitions, and it just worked. There was no explanation in these papers, no theoretical follow-up, but this was done several times, and every time it was done, it seemed to work. So we said, let's just try. Let's see if it will work for us too, even though the mechanism was not understood. And only after our results were published is there started to be some theoretical understanding of why these systems end up creating MOTs. This was nice work done by Mike Tarbett. So let's explain how we do it. In our case, with all the full complexity of strontium fluoride, with its spin rotation and hyperfine structure in the ground state, the excited state has very close to 0 G factor, no hyperfine splitting. There's a level structure in the excited state. The ground state has Zeeman shifts. G factor is of order 1, just like it is in an alkali atom. So we apply our laser with 4 sidebands from electro-optic modulators. They're all detuned so that each laser is detuned to the red of every individual line. We apply one beam, one laser with 4 frequencies, and all of them have sigma minus polarization. And you can see that is in accord with the picture where this Zeeman sublevel is shifted closer to resonance for the sigma minus beam. Same with this one. This one, there's no Zeeman shift, so it doesn't matter. But this one has done the wrong thing. Here we've been Zeeman shifted to the level that has the wrong polarization. So in order to fix that problem, we add another laser to the experiment with the correct polarization, or what we thought would be the correct polarization, sigma plus polarization, that comes closer to resonance with the Zeeman shifted level here. So that just adds one more laser to the experiment and seems to have the property that the Zeeman shifts push us closer to resonance with a beam that pushes us towards the center of the Mott. The actual experiment looks like this. Our slowed strontium fluoride beam coming from left to right. There's a standard Mott chamber with standard magnetic field gradient coils. Because we knew the experiment is very hungry for power, we didn't have the usual 3 or 6 beam Mott. We took a single set of laser beams, all the cycling and repumping lasers, and wrapped them around the whole apparatus in a single, very long, complicated path that conserved the power, but made alignment tricky. Nevertheless, it worked. And again, here's the idea. And here's the results. So this is an image from our original Motts. This is just fluorescence detection. I'll point out that from molecular physicists, the ability to do this imaging by using cycling fluorescence, by scattering tens or hundreds of thousands of photons for each molecule is revolutionary. Ordinarily, we're lucky to get 1 photon per molecule, so just being able to make these images was quite amazing. But you can see, we very clearly have a trapped cloud here. On the other hand, it looks a little weird. It's big by Mott standards, almost a centimeter in dimension. The temperature we were able to measure was about 2 millikelvin. We had about 300 molecules in the trap. The lifetime was very short, about 50 milliseconds. And ultimately, we understood that the reason this Mott was so big and fluffy is because the restoring force was very tiny, much smaller than in typical atomic Motts. Again, because we didn't understand the theoretical mechanism, that was a bit of a mystery until Mike Tarlett's paper came out and was able to give some understanding of why the forces are so weak and suggest that a different polarization scheme would give us a tighter Mott. So essentially what Mike Tarlett's theoretical analysis showed is that the principle that we were using of trying to tune our lasers to be Zeeman shifted into resonance was the wrong principle. That in fact the restoring force is only because this excited state has a small but not quite 0 G factor. In our case, the G factor of this state is about minus 0.1. But that small Zeeman splitting in the excited state breaks the symmetry between confining and anti-confining transitions. And essentially that's what evades the theorem from our apprentice's old paper that said the force should vanish. Essentially what Tarlett's analysis said is that the polarization that you want has nothing to do with the Zeeman shifts in the ground state. It has only to do with the Zeeman shifts in the excited state and whether delta F changes by -1, 0, or +1. So what he suggested was this was the correct polarization scheme. If you compare it to our original polarization scheme, for 2 of the transitions, by sheer dumb luck, we happen to have the right polarization. For 2 of them, we had the wrong polarization. So we had 2 anti-trapping beams and 2 trapping beams, and the net result was a very weak trapping force that allowed us to see a Mott. But going to this alternative scheme gave us a much better signal, much more intense signals, longer lifetimes and such. We were able to do a number of things with this. For example, we could measure the trapping frequency by deliberately offsetting the Mott and watching it bounce in the trap. You've never seen this for an atomic Mott because in atomic Motts, the damping forces are so strong that this motion would be strongly overdamped. But here the trapping and the damping are comparable, so you actually see some bouncing. But the bottom line is that using this new polarization scheme gave us about a 20 times increase in the spring constant for the restoring force, an increase but not as much of an increase in the damping. The lifetime got longer because we weren't boiling over the edges of the trap. We got more molecules, up to a whopping 500, but the temperature got much higher, went from 2 millikelvin to 13 millikelvin. And there's still no theoretical explanation that makes sense for why the temperature got higher. We don't understand it. So for any theorists in the room, this doesn't feel like a sexy problem, but it's a vexing one. Yeah.
So does the theory paper also explain how subdoppler cooling mechanisms work?
No. No. So this
also confusing based on the level structure. Because normally I would think that you have to have also free states to the excited state.
Yeah. So I would say, to me, we didn't even try to do this theoretical analysis because it explicitly was ignoring subdoppler effects, which we thought should be important. And nevertheless, it's clearly got some qualitative features that are correct. Mike is now at work at a more sophisticated model that does take into account the polarization gradients and potential subdoppler cooling, but the results aren't complete for that yet. Sorry, was there another question? So this was, on one hand, encouraging. We have a better trap. On the other hand, because the temperature was so much higher, the phase space density in this new trap was unchanged. So it didn't seem like a step sideways rather than a definite step forward. So then we decided to try a principle that was first demonstrated by Jim Yee's group in 2 dimensions, to make a MOT that eliminates the dark states in a very transparent way, which is you start with a polarization that is Zeeman shifted, or you start with a polarization such that you're Zeeman shifted into resonance. When you pump to a dark state, you don't stay there for very long. Once you get there, you rapidly switch the polarization, but at the same time you have to switch the magnetic field gradient in your MOT. So the idea here is pretty simple and straightforward. It's complicated in practice because you need to switch this about as often as you're scattering photons. In other words, you need to be able to switch your magnetic field gradient at megahertz rates, which is non-trivial. And the hope was from this that essentially all the photons that you scatter here are always pushing you in the right direction. You don't need to depend on this Zeeman shift in the excited state. And Mike Tarbott's model and any simple understanding would tell you that you should get a tighter confinement with this scheme than we got from any of our more conventional MOT schemes. We've set this up now. As I mentioned, there's a real technical challenge to make this switched magnetic field. So the idea is we're sinusoidally oscillating our magnetic field gradient of about 10 Gauss per centimeter at a frequency of order of megahertz. We're simultaneously switching the polarization from sigma plus to sigma minus. That's easy with an EOM. But the MOT coils, here's a picture of our MOT coils. They're in-vacuum coils, copper coils on ceramic aluminum nitride boards for heat conduction. In order to get big MOT beams through here, these things, which we know we need to load or trap, well, these things have a big inductance. Since they have a big inductance and a high frequency and a pretty high current, we have to have pretty high voltages across this on the order of kilovolts to run enough current through it to get the magnetic field gradients that we want. So that's tricky, to say the least. Here we got a tremendous amount of help from Nick Hutzler, who was in John Doyle's group then, because they were already working on this. He guided a lot of our design principles. But the basic idea is we make a resonant tank circuit with capacitors tuned to make it resonant at the frequency we want and for impedance matching. In the end, we were able to get the currents that we needed at the frequencies we wanted by putting in about 100 watts of RF power. That's about the same as the Yale radio station, but it works. And in order to withstand the high voltage, we found that we needed these vacuum tunable capacitors that are Soviet-era surplus from radio transmitters, widely available on eBay. Right. So here's this picture. We're oscillating the magnetic field sinusoidally, switching the polarization. And the idea is that we want the polarization to be synced with the magnetic field. Obviously, the phase, the relative phase, has to be correct. If you have the wrong phase, then you'll be anti-trapping. So we expect the confining force to depend on this phase shift between the magnetic field and the polarization switching. And here's typical data. Here's an image of the MOT and the fluorescent signal from the MOT as a function of the phase. And as expected, we see a nice peak at phase of 0 when the magnetic field and the polarization are with the correct phase. If you go off phase, then we don't get anything trapped. So that made us believe that this basic mechanism was working. We made some pretty detailed studies of what's going on here because it's not obvious in many ways what's happening. But some of the key results is as we crank up the laser power, the more molecules we get, not too surprisingly. Under the best conditions, we get 3 to 4 times more molecules in this MOT than we had in our improved DC MOT, what we call the DC star MOT. DC is the original one, DC star is the one with the new polarization configuration. Basically, this says if you want more molecules, you need higher laser power. This is showing the molecule number as a function of laser power for the DC star MOT, the improved polarization one, and different switching rates for the RF MOT. Notice that 110 kilohertz switching rate should be slower than the scattering rate. This should be more analogous to a DC MOT, according to our understanding. These are all on the order of the scattering rates. We expected them to be roughly comparable to each other. And you can see, maybe a little surprisingly, the low frequency switching doesn't seem very different from the high frequency switching, but they all seem better than the DC case. Okay, that's curious. What about other properties of this trap? So we looked at the lifetime of the trap, and we found something that came as quite a surprise, which is our DC MOT still had a rather short lifetime, only a little over 100 microseconds. And as we turned the laser power down, here encoded in the scattering rate of the molecules, the lifetime went to 0 very rapidly. A little bit less laser power and the trap just went away. By contrast, the switched MOT, the RF MOT, the lifetime went up as we turned the laser power down until it finally plateaued at about half a second. As the power gets higher, we finally understood for the RF MOTs, we were essentially cycling so fast that we were leaking in, we had some branching into a state that we were not pumping out of. But at the low power, this half-second rate, we don't really understand what's limiting that at this point. Half-second lifetime. But it's still comparable to an atomic MOT. So that looks sort of like what we're used to for atomic systems. The reason why the DC MOTs go away so quickly as we turn the laser power down is not well understood. If we think about how tightly we've trapped, again, as a function of the scattering rate, much to our surprise, we had expected that switching the MOT would give us a tighter trap, and we see that's not true at all. If anything, it's ever so slightly weaker than some of the DC cases, and perhaps not surprisingly, as you turn the laser power down, the trap gets weaker. Of course, the DC MOTs, if you turn the laser power down, the trap goes away entirely. But for the switch MOT, it doesn't go away, it just gets weaker. So that's interesting. Then we also measured the temperature as a function of the laser power, again encoded with the scattering rate. And here we found something extremely striking, which is the temperature goes way down as we go to lower scattering rates. Here is the only place, and the temperature is the only place where we see a difference between the slowly switched MOT and the rapidly switched MOTs. But for the rapidly switched MOTs, if we go down to low laser powers, we get temperatures down as low as 400 microkelvin. So getting pretty close to the Doppler temperature. I'd say that there is an analogy here for MOTs made of alkaline earth atoms, where there's no subdoppler cooling mechanism at play, and there are stimulated force heating mechanisms that cause the temperature to go up as you turn up the laser power in those MOTs. We think that's probably at least part of the story of what's going on here. But still, there's a lot that's not understood. But finally, we plotted the phase space density, again, as a function of laser power or scattering rate. Here we followed a protocol where we loaded the mod at high power to get a large number of molecules, and then reduced the power to trap at low temperature. And we saw we didn't lose any molecules by doing that. The bottom line is, compared to what we had before with our unswitched mods, we're now able to make mods with a 1,000-fold increase in phase space density compared to anything we had before. So that's real progress. And again, we're now at temperatures that are quite comparable to what we're used to for atom mods. So here's a quick summary of what we've done with molecular mods so far. Our initial mods, now on the scale of our new ones, we can barely see at all. Now we're up to about 2,000 atoms, lifetimes of half a millisecond, temperatures of 400 microkelvin. Phase space density, of course, by atomic standards, is tiny because our number of molecules is so small. But everything else, the trapping frequency is only a little worse than it is for atoms. Everything else is comparable except the molecule number. So this really starts to feel more and more like what we know and love for atomic physics, and starts to make us think of this as potentially a tool for doing physics. So let me just pause here and give you a little bit of summary and outlook. I told you that we were able to make the first molecular mods. We were able to make really ultra-cold molecules, sub-millikelvin molecules, using this RF switched mod technique. There's a lot that we don't understand about this, but it's experimentally now a robust and well-characterized tool. And now we're on the pathway to taking our molecules to higher phase space density, doing things like loading more molecules by guiding them while we're slowing them, doing some sub-Doppler cooling and loading them into a conservative trap, where hopefully we'll be able to do some sympathetic cooling with atoms. Though I'll point out, if there are theorists in the crowd, the question of how sympathetic cooling will work at these temperatures, for example, for magnetically trappable atoms, alkali atoms with strontium fluoride, is still not well understood. With that said, it's been gratifying that lots of folks in the community have been starting to think about how to use these techniques to do other interesting physics. So it's been pointed out, for example, that the system of bialkali molecules, where it's now several groups have samples of molecules near quantum degeneracy, but still not quantum degenerate polar molecule gases. Shininoi's group pointed out that systematically in these bialkali molecules, there are closed transitions that are suitable for laser cooling, and they also have very narrow lines, so the Doppler temperatures in these transitions are cold enough that it might be helpful for cooling these gases further. Several groups, including our own, have been thinking about doing precision measurements, such as EDM experiments, by laser cooling. Here there's a proposal from Ed Hines' group to make a fountain of molecules to do an electron EDM experiment. There are ideas for using these techniques to assemble larger molecules out of laser-cooled molecules and atoms, or molecules and molecules. We already heard from Yvonne about the beautiful work that's going on in the Doyle group, and suggestions from other groups that laser cooling may be surprisingly applicable even to more complicated molecules, triatomics, or even more complicated systems. And I would say that's a tremendous surprise and very interesting. There are ideas for how to make ultra-cold atoms, such as hydrogen or fluorine, by dissociating molecules that use laser-cooled. And then something that Yvonne also mentioned that we think is quite interesting is the possibility that laser slowing and even laser cooling may be possible without needing a cycling transition. So there are some very, very provocative results from Hal Metcalf's group showing that bichromatic forces with lasers can give you cooling without spontaneous emission. And this opens a lot of very interesting potential pathways. So I probably won't have time to tell you about our work on this, but I'll mention this very briefly. We've now started working with Larry Hunter at Amherst College on a new species, which is a nice candidate for laser cooling. It's thallium fluoride. This is quite different from all the molecules that other people are using so far, in that it doesn't have an unpaired valence electron. The ground state actually is a closed shell, a singlet state. But you can excite it with the analog of an intercombination line in an alkaline earth atom, singlet sigma to triplet pi transition. And this has exceptionally diagonal Frank-Condon factors. So you can scatter over 200 or around 200 photons without a need for a single repumping laser. The measured lifetime is short enough to do fairly rapid cycling. You can do transverse cooling with a single repumping laser. They're annoyingly in the ultraviolet, but if you put that aside, it looks even better than the molecules we've used so far. But slowing will be difficult. It's also interesting, unlike our strontium fluoride molecules, here the level structure allows you to use a standard Zeeman slower like we're used to for atoms. And this guy, as I mentioned, is chemically distinct from other laser cooling species. It's not a free radical, it doesn't have an unpaired spin. But the reason we're most interested in this is for possible application to a search for a nuclear shift moment, which in the interest of time I'll say is almost like a nuclear electric dipole moment. The physics is analogous to what you would have. So it's like our electron-electric dipole moment ACME experiment, but instead looking at a nucleus instead of at an electron. And we've now started a new experiment that we're calling Centrex, which is a new search for this shift moment, a nuclear analog to the electron-electric dipole moment. This comes about just like the electron EDM if there's time reversal or CP violation. We're competing with the state-of-the-art, which is an experiment done at Seattle using mercury-199 atoms. The Seattle experiment is a tremendously powerful experiment. It's already sensitive to new physics at scales above the TeV scale. So as John said, our ACME experiment is putting pressure on models of physics that the LHC would expect to see signals from. And likewise, this mercury-199 experiment has also been putting pressure on models that predict new physics at the TeV scale. But we want to go further. And the basic idea is very similar to the idea of our ACME experiment, where by putting our nucleus in a molecule rather than in an atom, very roughly speaking, I'm shoving some stuff under the rug here, but very roughly speaking, the nuclear shift moment, which is like a nuclear EDM, will react to something like an internal electric field, cause the spin to precess around, and we try to measure this precession frequency. And the point is that this interaction in the polarized molecule is something like 10 to the 4 or 10 to the 5 times bigger than it is in mercury atoms. So the molecules really amplify this effect by a gigantic factor. And our goal is to use this enhancement to probe well above the TeV scale, look for new physics at energies well beyond what the LHC can probe. So the basic idea looks like this. The first generation will be a molecular beam experiment, very similar to the ACME experiment. It leverages a lot of the techniques that we've developed for our electron EDM search here. It has a few extra features. We can have a much longer interaction region because we're using ground state molecules, unlike the metastable state in ACME. We'll add an electrostatic quadrupole lens that focuses the molecular beam. We're doing this in a collaboration with folks at Columbia and UMass. We've just got some funding from the Templeton Foundation, of all places, to do this physics, which is quite interesting. But then this, much like ACME, this has natural improvements in second and third generation. So for example, if we add transverse laser cooling, we can get much better statistics for the experiment. And then the third generation, we think may be possible by slowing the beam and eventually trapping it to do an EDM experiment with trapped molecules. So there are lots of questions still to be answered about that. Thallium fluoride is the molecule that we've chosen. As I mentioned, it's a good molecule for laser cooling. It's also a molecule that's been studied in tremendous detail. So there's lots of details about the molecular structure that are known. A lot of this is from experiments that were done in the 1980s by Norman Ramsey here at Harvard, and also by Ed Hines when he was at Yale, where they used thallium fluoride molecules, but with much older and less advanced technology than we'll use here. One of the nice features is, in this first generation experiment, we won't even try to do laser cooling, But we will use this cycling transition so that we can detect the molecules, scatter many, many photons so that we're sure to collect at least one photon per molecule, and that will give us 100% detection efficiency, allow us to cool the rotational degrees of freedom very efficiently, and then eventually in later generations do laser cooling and trapping. There are other nice features that allow us to suppress systematic effects in this experiment, but since I'm out of time, I won't talk about those. The bottom line here is that by scaling from the ACME experiment, we think we can have frequency sensitivity at the level of about 200 nanohertz. What that means is we'll be probing lots of new physics such as quark EDMs, quark chromo EDMs, and so forth. And the bottom line, so this is sort of a complicated table, but the bottom line is we'll be more sensitive by factors of 10 to 30, according to our projections, to many of these underlying physical mechanisms associated with physics at the TeV scale than any previous experiment. So we're quite excited about this. It's sort of a new frontier in precision measurements using molecules, but a new frontier in precision measurements overall. Right. So let me just end there. I'll skip this because it's not that crucial, and get to the end where so I've told you about our work cooling and trapping molecules. I'm particularly excited about the applications of these to precision measurements, in particular this new experiment to look for nuclear hadronic CP violation using molecules. But yeah, we think things are opening up in an interesting direction based on these techniques. And with that, I'll end and just point out that the work was done by a tremendous group of students in my group. The latest strontium fluoride results were done by Danny McCarran, Eric Norgard, Matt Steinecker, and Eustace Edwards. I don't know if John Barry is in the audience, but many of you may know John. Hey John. So John did a lot of the early work while he was a grad student in my group that I showed you here, and he should receive much of the credit for it. So with that, I'll thank you for your attention.
Questions?
Is the initial molecule number of 2000 mainly limited, or final number, mainly limited by just the capture range from the initial cooling state?
I would say it's a combination of the capture range, which we don't have a good measurement of, but even more so, it's that we know that for any reasonable capture range, we just are not delivering many molecules at that velocity in the volume where the MOT lasers exist. And it's because we have to depend on this white light slowing technique, which means that we're usually slowing things down either before the trap or after the trap, and only occasionally in the volume where the MOT lasers live. So yeah, I feel like that molecule number is overwhelmingly limited by the fact that our slowing method is not efficient at delivering molecules where they count.
Kind of sharpen it up a little bit. Do you have an efficiency, like how many molecules that are in the right place and are actually getting into the MOT? Sorry, in the right place, in the right velocity range, getting into the MOT?
Yeah, so the problem is that we haven't come up with a good way to measure what the capture velocity is. So with, I would say, very hand-waving estimates of that, our efficiency is pretty good, but I'm not sure that I trust our hand-waving estimates of what the capture velocity is. Yeah, so that it's an open question to some extent.
Is D1 continuously there, so the molecular source continues, or is this pulsed?
No, it's pulsed. Yeah, it's pulsed, and right now the repetition rate is fairly low for some technical reasons. So yeah, we haven't tried, for example, doing multiple loading of the MOT. Yeah, so this is one-shot loading.
So this is like so you ablate these molecules, and I have to imagine there's like a stream of molecules coming. Some of them make it into the trap.
Yeah, and most of them don't. Yeah.
Sometime, and then they go away. And then
Yeah.
There's another stream of molecules.
Yeah, that's right. So now our trap lifetimes are comparable to the rate at which we can pulse the system. Though again, we haven't actually tried multiple loading, but our trap lifetimes are half a second now. And we can easily run the system at a few hertz. So we typically run more at 1 hertz for
So
some
then at
technical
some point
reasons.
you might expect that there's like a continuous number of molecules.
Yeah, so there, I would say,
Nonsensical.
it's not nonsensical, though there are, I would say, for reasons that are not well understood, as you turn up the repetition rate of the source, the flux of molecules per pulse goes down quite rapidly. And some of that, a little bit of that is just heating of the cryogenic source because you're dumping too much power into it. But the decline in the number of molecules per pulse is much more rapid as a function of repetition rate than you would expect from that. And there's not a good understanding of what it is that causes the molecule flux to go down as you turn up the repetition rate. For example, in our Acme experiment, we can go up to 50 hertz repetition rate just fine. And then at 100 hertz, it starts to roll over. So there's something different about the ablation dynamics between strontium fluoride and thorium oxide that we don't understand.
Yeah, just to add to that, there's basically a 3-order of magnitude difference in the production of molecules via this ablation in a cryogenic source. The 3-order magnitude difference between the best and the worst.
And
Nobody
strontium
really
fluoride is
understands it.
sort of in the middle.
Yeah.
Yeah, but yeah, we can't predict what's going to happen.
Speaking further to this point of the flux decreasing as you increase repetition rate, we see the exact same thing in our buffer gas source with barium fluoride, which is very similar to strontium fluoride. And our kind of explanation for it has always been localized heating causing localized phase changes to some other phase, some other solid phase or glass phase that does not create plasma blend as well. And so when we ran at 1 hertz, we could do that forever. If we tried to run even at 5 hertz, it was just nonsense. But we found that we could overcome that with a galvanometer to rapidly scan the laser placement on the target. Have you tried anything like that?
We have, and I would say we did not have the success that you're describing, but I'd be really interested to talk and see if you're doing something different from what we did.
Okay.
So for thorium oxide, where we run at 50 hertz, there we don't have to rapidly scan, but when you're hitting that fast, you deplete the target pretty quickly, so we do have to scan fairly quickly.
Sort of following up on this, but in the context of thallium fluoride, have you had a chance yet to try to make a beam of thallium fluoride?
Yes, so we just made our first beam of thallium fluoride about a week ago. I would say because ablation is sort of a black box, we were concerned about this. We turned it on, and with no optimization whatsoever, we immediately got a flux that was very similar to thorium oxide, which is about the best we've seen of any molecule. Thallium fluoride is very interesting because we don't have to break or make any bonds. It just vaporizes as thallium fluoride. And actually, the boiling point is only about 500 C. So we think it may be possible to do a more gentle, instead of ablation, which is a very non-equilibrium process, we think it may be possible to do continuous wave heating where we're literally thermally vaporizing the source. And we're about to try that. We're optimistic we're going to actually get a much bigger flux, but we'll see.
I'm not a good person to chair this because I'm just going to keep on saying it.
This might be a very naive question, but if the Mach, seems very challenging, but if that works, could you imagine doing something like a slower, which would give you that position selectivity that you don't have with the white light source?
Yeah, so in principle, yeah, but when we've tried to put in numbers for what it takes to make that work, it's beyond horrifying. We just can't seem to do it. But it is interesting. Things like thallium fluoride, where there's a Zeeman shift in the excited state but not in the ground state, there Zeeman slower should just work in the way that we know and love. So we think there are other tricks to do for molecules like strontium fluoride to help get around this problem.
Yeah, I think that you're working on some of the tricks. There's a lot of people thinking about this transition from, say, 50 meters per second to essentially 10 meters per second. And Dave mentioned some of them, like with the start deceleration. There's also magnetic deceleration, which you also mentioned. but everybody understands that that's the hard part.
Yeah, that's the weak link in this whole process. The mod, in some sense, there was a lot of engineering that went into it, but now it works, and I think it would not be hard to replicate it. But the slowing is still the weakest link in the whole chain.
Could you comment on the spring constant measurement for the RF mod?
Uh-huh.
So in the DC mod, just displaced it and looked at this bouncing, but
Right.
how is that done for the RF?
Right, so for the RF mod, we couldn't figure out how to displace it because we didn't have transverse RF coils to push it around. So there we just did time flight expansion imaging and then used equipartition theorem to back out what the trap was. So we could measure the temperature from time of flight expansion, and then knowing the temperature and knowing the size, equipartition told us what the spring constant was. So not as direct a measurement as we had for the DC mods, but we had also done similar things in the DC mods, and the techniques always agreed with each other. It's just kind of cool to see them on bouncing, so I like to share that data.
Any other questions? Okay, let's thank Dave again.